Hello, my name is Sara Inani, and this is my Physics Lab 2 observations. In this lab, we are observing the fall of an object somewhat slowly. As compared to the previous lab, our Fnet is not assumed zero, but A, the gravitational pull, and B, the gravitational pull plus the drag force. I will compare the graph of position y versus time for three situations: the experimental situation observed on tracker, and the two situations that I stated above using GlowScript. In this lab, we are testing Newton's second law in all of these cases. There is acceleration, thus Fnet is not equal to zero. Using Newton's second law, these are the formulas that will be used. So let's get started. I am using Tracker, which is a software that helps me analyze the motions that I have recorded on my video. I am observing the motion of a falling air-filled ball. Here is a snapshot of my tracker and the values for my y coordinates and the graph for my position versus time. The final time, which I have not shown above, is 1.1 seconds. Like said before, the object that I use is an air-filled ball. The ball is 10 centimeters in diameter. The fact that it is filled with air makes it complicated, as we shall see in the next few slides when graphing the computational model. This is due to the fact that I'm calculating drag with an air-filled object. Next, I am using GlowScript. It is a program that helps me compute models and simulations, and it helps me observe my motions. Here are snippets of my coding. We have been given the original code, but I updated it with the values that I've had. G is set to 9.8. My J hat is pointing in the positive y direction. The values of B have been found through trial and error. I have inputted the formulas for weight and drag by applying Newton's second law. Image 1 is without drag, while image 2 is with drag. My blue arrows show drag, while the orange one shows gravity. The length of arrow for drag and gravity update accordingly. Interestingly, for my object, in image 2, there is a fixed time when my drag force arrow and my gravitational arrow appear almost of the same length. Here's my graph. The blue shows the analysis from tracker. My yellows show the model without drag, while my red show the model with drag. The red line is much closer than the observed blue line, which shows that drag force did play a very crucial role in determining the motion of my falling object. The fact that I threw an air-filled ball made a big difference in y direction wise. The drag force, as seen in the previous slide, was much larger. Thus, while in real life my object was falling down very slowly, a ball would have fallen for a much longer distance. Thus, there is a large difference. The difference between the blue and the red line may be attributed to any other air source being present in the room. We're only considering air drag force over here, but there could be other sources of moving air in my room, which could be the reason for the overestimation in the tracker, that is, the blue line. Also, the camera angle that I recorded with, the axes were not 100% aligned, and the camera angle was tilted as well. Question. Examine the velocity versus time predicted by your models with and without drag. Which model predict a terminal velocity? Discuss briefly. As seen before, I had defined terminal velocity as the maximum velocity where air resistance and gravity cut each other out, which means that velocity can no longer go faster, or it can no longer speed up. As seen in the two images, in the first one, terminal velocity is not reached, while in the second one, terminal velocity is reached. The second image started reaching no acceleration, which means that it reached its maximum velocity. Question. What if, imagine that the object was initially thrown downwards? Would the terminal velocity in this case be same or different from the case where the same object was initially dropped from rest? So here, I used GlowScript, where I put the initial velocity as 0, -2, 0. As seen, we still do reach a terminal velocity, it's just that we reach the terminal velocity faster. Thank you.